I'm very, very pleased to be welcoming Antonietta Mira to give this seminar. And Professor Mira has been one of our strong collaborators with the group here at QUT. She's been collaborating for a number of years, been to Australia a number of times, had people from QUT visit her university as well, and she's extremely active, well known internationally on a number of international societies and committees, one of the best known Bayesians and computational statisticians in the world. So it's a great honour to have Antonietta be able to present to us today, and I thank you for your time. Antonietta, I'm going to hand over to you, and the floor's yours.
Well, thanks, Carrie. Well, thanks for the invitation. It's a pleasure to be here. Yeah, I very much enjoy my time in Brisbane and my collaborations with all of you. And by now we have a stack of papers piling up, and I hope it will continue to grow despite the difficulties in actual visits. But we have all learned that distant learning and working does work. So today I will catch up or continue with a presentation that I gave at Base on the Beach in 2019. And since then, we have progressed a lot, and some of the papers are on their way also with researchers, even very young ones from QUT. And specifically, besides Carrie, I've been collaborating on this research line with Abhishek Varghese and Edgar Santos Fernandez. And I will, at the end, talk about the two very interesting applications that we are developing with them. My other collaborators are physicists from SISA in Trieste, Italy, Michele Allegra and Elena Facco and Alessandro Laio, plus a former PhD student of mine and now postdoc at UC Irvine, Francesco Denti. And I would say that Francesco and Alessandro, well, and the physicists are the driving force on the methodological aspects of this research, while the QUT group has been very, very good at picking up this general idea of an intrinsic dimension or dimensions and come up with a very interesting application that themselves have sparked new methodological research lines. So it's really a pleasure to continue this conversation with you that started a couple of years ago. So the first question is, if I show you these 3D data points, can you learn or understand what was the data generating process? Well, it's not easy. They seem sort of uniform, scattered over this 3D space, except that we see maybe a line here, which is a little suspicious, and you can sort of see it here in this projection. But those points seem like genuinely in 3 dimensions, especially if you look at this plot on the left. Well, as a matter of fact, those plots are actually 2-dimensional. So they were obtained from an X and Y random points, and then they were transformed in a 3D set, because this sort of gives a clear idea of what's going on. This is actually a 2D image. Points are on a Swiss roll embedded in a 3D space. So this is what we call a 2-dimensional embedding in manifold embedded in a 3-dimensional space. And what we are trying to find is this 2D, which is the intrinsic dimension of the data. So this is what we call the intrinsic dimension of the data. So the data is really two-dimensional, embedded in a three-dimensional space. So 3 in this case is capital D, and 2 is lowercase d, is what we call the intrinsic dimension of the data. So this is fairly typical in statistics. We collect data in capital D dimension, but really there is a small number of variables, lowercase d, that is often sufficient to effectively tell us features of the data, minimizing the information loss. And in the specific case below, the information loss was 0 because the data was genuinely living in a two-dimensional manifold. But often there is some loss of information because there's noise added to the data. So we call this lowercase d the intrinsic dimension of the data, and this is what today I will tell you how to find. Sometimes the intrinsic dimension of the data can vary within the same data set. And by finding the intrinsic dimension, we learn insight on the data structure. And therefore, what we are really after is searching for the local intrinsic dimension. Here's another plot that is not supposed to be rotating, so that's fine. Here we have 1,000 observations generated from 5 Gaussian distributions of different dimensions, 1, 2, 4, 5, and 9. Some of them are overlapping. Here you see the line in dimension 1, and here in this plot, you see those data that really collected on a 9-dimensional space projected on the first 3 dimensions. And again, what we are after here is a way to say, look, this data really contains 5 submanifolds of dimension 1, the black that is embedded here, and then 2, 4, 5, and 9. This is what we're trying to find at the end of the day. So the number of submanifolds and their respective dimensions, because this will be able to segmentate or cluster the data, and those clusters have interesting features that are discovered with the knowledge domain expert, that is, the experts that know how the data have been collected. So we have applied this methodology in very different domains, some of them biomedical. In particular, we manage by looking at protein configurations that move from a folded to an unfolded state, that the intrinsic dimension characterize the folded versus the unfolded state. So in this case, our methodology tells us, look, there are 2 submanifolds, and most of the proteins in their folded configuration live in one of them, and most of the proteins in the unfolded configuration live in the other one of them. And notice that before starting, we didn't tell the algorithm that there were actually 2 types of configuration. This comes out after we managed to segment and cluster the data using the intrinsic dimension. Similarly, with brain imaging data, we identify 2 submanifolds, and it turns out that the active regions of the brain, where the fMRI was taken, the person was doing something, are clustered in a region, and the non-active in a manifold, and the non-active regions are clustered in another manifold. Similarly, we have gene expression data, some of patients, some of controls, and with the intrinsic dimension, we managed to separate them. So there's a simple topological feature, the intrinsic dimension, that manages to uncover a rich data structure. We move from biomedical applications to other type of application. We look at balance sheets data, and we can cluster companies depending on their different financial risk. We have looked at basketball data. This is with Edgar and Kerry and Francesco. And somehow the intrinsic dimension tells us something about winning versus losing strategies. We've looked at the output of MCMC simulation, and the intrinsic dimension tells us whether the model of which the MCMC simulation is helping us infer the parameter is well identified or not. And with Abhishek Verghese, again with Kerry and Francesco, we look at COVID-19 data telling us about the evolution of the pandemic, and the intrinsic dimension tells us about class-specific non-pharmaceutical intervention. So again, outside biology, in sport, finance, and different type of data, the intrinsic dimension allows us to tell interesting things about the data and uncover structure that might or might not be known ahead of time. So here's the agenda for today's talk. I will remind you about the 2 nearest neighbor, which was the topic of this talk approximately 2 years ago. Here we create an estimator for the intrinsic dimension by looking at ratios of distances of first to second nearest neighbors of every point in the state space. And there is a maximum likelihood estimator of the 2 nearest neighbor, and this is a Bayesian version of the 2 nearest neighbor estimator. The MLE 2 nearest neighbor was something that the physicists developed themselves, and then I joined their team, and we moved into the Bayesian direction. Then recently we developed the CRIDE and the GRIDE estimator of the intrinsic dimension, acronym that stand for consecutive ratios and generalized ratio intrinsic dimension estimators. And then we have the Hidalgo version of the 2 nearest neighbor that allows us to handle situations when there is more than one submanifold embedded in the data. So the first 3 estimators handle the case when there is a single submanifold, as in the Swiss roll. The Hidalgo and the Bayesian parametric Hidalgo allows us to uncover structures where there's more than one submanifold embedded in the data. And the development relative to the older version of this talk, the earlier version, is that CRIDE and GRIDE estimators of the intrinsic dimension are more robust to noisy measurement, more relative to the original 2 nearest neighbor estimator, and allow us to study the evolution of the intrinsic dimension as a function of the scale of the distances between points in the data set. And as I already mentioned, Hidalgo and the BNP, Bayesian parametric version of Hidalgo, allow us to uncover the structure if there's more than one intrinsic dimension, that is, if there's more than one submanifold. So I'm going to go through this theoretical development first, and then I will tell you about some of the applications. So Kerry, I have about an hour, is that right?
Yeah, that's right. Sorry, I was on mute. Yep.
Thanks. Okay, so here's another picture that tells you about the intrinsic dimension visually. So here we have data collected in a 3D space that really lives on a 2-dimensional manifold. So capital D is 3, lowercase d, the intrinsic dimension is 2, and this is what we are trying to find. Here there is a single submanifold where all the data lives. In this case, the submanifold is linearizable. So if I stretch it, it becomes like a flat surface. And finding a flat surface in a set of data is something that we know how to handle fairly well. The intrinsic dimension methodology that we develop allow us to uncover submanifolds that are not linearizable. For example, if they have holes, we can still identify them. And the message of this talk is that accounting for the intrinsic dimension can improve the statistical analysis as such, identifying patterns and classifying the data in manifolds where the data has homogeneous characteristics. So we believe that the intrinsic dimension should be a pre-step in any statistical analysis. So you identify or cluster points that live in different submanifolds, and then you do your analysis within those submanifolds. So how do we estimate the intrinsic dimension? I'm going to focus on the statistical approach, While if you search the literature, there are other type of approaches, but being a statistician and having mentioned the other approaches in my previous talk, I will today focus on the statistical approach, which is where we gave contribution. So we assume the underlying assumption that will go throughout this talk is that the data are generated as a configuration from a Poisson point process, which we'll indicate by PP, with a true intensity function of the Poisson, which we will call rho. And throughout this talk, we will assume that we have a distance that we call delta that takes values on R plus, defined among the data points, which we'll indicate with xi, and we assume that we have n data points. So I will be consistent, and this will be the notation. So we always assume that there's a point, Poisson process, and that we have defined a distance. So whatever distance it is up to you. We don't care. So you give me your data and a distance, and I will give you a methodology to find those submanifolds and their intrinsic dimension. So at the end of the day, I will be able to tell you which data point belongs to which submanifold and what is therefore the intrinsic dimension of that specific data point. And then we cluster together data points that have the same intrinsic dimension. Notice that the intrinsic dimension is a fractional intrinsic dimension. It's not an integer number. So the theory relies on the fact that if for every point I or any point I, we look at the number of other points that are within distance R from that point. So if we sum the indicator function of the delta ij being less than R, this quantity scales, of course, with R, the radius of the ball that we built around the point I, D, the intrinsic dimension of the data, assuming here that there is only one intrinsic dimension, so all data is in a single manifold, submanifold, and rho, the intensity function that typically depends on X. Now, under the assumption that rho is everywhere constant in the Poisson process, which is a strong assumption, then we can estimate D by using the fact that the number of points within distance R of any point depends on the intrinsic dimension. And we can estimate D either by maximum likelihood or by a simple linear fit. And this works as long as rho, the intensity of the Poisson process, is constant everywhere. The problem is when rho varies, this methodology fails dramatically. And here's where we intervene. So the colleagues from physics managed to...
Hello? Wszystko dobrze, a pani zadzwoniła, tata był ok, ale kazał mi on ciebie odebrać, żeby cię trochę przestraszyć. Wszystko dobrze, nie bój się, right?
I don't think this is me.
Next to his wife, yeah?
Is there somebody else
It's
on
okay.
the line? Can everybody please make sure that their mics are muted?
Okay, thanks. Okay. So the idea is that here the problem is that this function depends on both D and rho, and we need to assume that rho is constant everywhere to be able to estimate D from this function of the data. Well, my colleagues, physicists from CISA University, managed to find a function of the data that depends only on D and not on rho. So we don't need to assume that rho, the intensity of the Poisson process, is constant everywhere, but only locally constant in the region containing the first two neighbors of a point, xi. So the assumption of the two nearest neighbor estimator is that data are regarded as a configuration from a Poisson point process with a density function rho, which is assumed to be only locally constant and not constant everywhere. And to describe this two nearest neighbor, we need a function of the data, and the function of the data looks for every point xi at the distance between the first nearest neighbor and the second nearest neighbor. Remember, you have to give me a distance function. Get that distance, I find the first and the second nearest neighbor, and I look at the RI1 is the distance between point I and its first nearest neighbors, and RI2, which is the distance from point I and its second nearest neighbor. So then we look at the ratio of those two distances. So namely, we look at RI2, distance to the second nearest neighbor from point I, and RI1 to the first nearest neighbor. And we look at this quantity mu I. And we managed to find, actually they managed to prove that the distribution of these mu i's, that are summaries of the data, is a Pareto distribution with parameter equal to D, which is the intrinsic dimension of the data. So this paper was published in Scientific Reports in 2017. So they assume that the mu's are independent. So they took a product of this Pareto distribution and derived a maximum likelihood estimator for the intrinsic dimension, which has this formula. And moreover, we can build a confidence interval for the intrinsic dimension at a certain confidence level, 1 minus alpha, the usual way, using here the quantile of the inverse gamma distribution. When I jumped in, I said, well, we can also be Bayesian, assuming a conjugate prior on the intrinsic dimension. And it turns out that the posterior, moving ourselves in a conjugate setting, is again a gamma distribution. We find the parameter of the gamma distribution, and so we can derive the Bayesian estimator of the intrinsic dimension as the posterior mean of this gamma distribution. And we can, of course, derive the credible intervals of the intrinsic dimension. So this is all nice if the assumptions are satisfied. So we see a very good fit unless the two assumptions that we made are not verified. And the two assumptions is that the dimension is constant on the scale of the two neighbors, and the dimension of, and there's a unique submanifold embedded in the data. The next step is to overcome this assumption. And here we move from the two nearest neighbor to Hidalgo. But before telling you about this step, removing this assumption, we worked on being more robust relative to the first assumption. And here comes the notion of working with not just the ratio of the first to the second nearest neighbor, but the ratio of consecutive neighbors of every data point. And here Francesco Denti managed to prove that not only the ratio of the second to the first distances is Pareto, but if you take the distance to the nth nearest neighbor divided by the distance to the nth minus 1 nearest neighbor, this quantity, which we call mu I L, also has a Pareto distribution, not with scale D, but with scale L minus 1D. And this holds true no matter how we pick L. So not only second to first, but for example, third to second, 8th to 7th nearest neighbor. All these distances have a Pareto distribution, and the parameter depends on D. And moreover, those ratios for every point I that we can store in a vector of dimension L are jointly independent. So we can use all these ratios, all these L ratios for all the N data points and come up with a new maximum likelihood estimator with the corresponding confidence interval and a new Bayesian estimator, again, putting a gamma prior on the intrinsic dimension, coming up with a closed form expression for the posterior, and therefore the Bayesian estimator will be simply the posterior mean of this gamma distribution. I'm assuming you're all Bayesians, having learned Bayesian statistics from Kerry and Chris Rovandi and all the wonderful colleagues at QUT. So I'm assuming you know what does it mean to be Bayesian, which means, in 2 words, coming out with a prior distribution on the parameter of interest, in this case, the intrinsic dimension, combining the prior with the likelihood using Bayes' theorem. That gives you the posterior distribution, which is the distribution of the parameter of interest given the data. Here, the data is the summary of the data that we have built through this ratio of consecutive distances. So here's the posterior distribution. Sometimes it has a closed form expression, sometimes it doesn't. Here, the posterior distribution does have a closed form expression, and the posterior mean is our Bayesian estimator, which is the what we would use as Bayesian instead of the maximum likelihood estimator. And the variance of the posterior distribution allows us to build credible intervals, which are the Bayesian counterpart of the confidence intervals. Good. This idea of using consecutive ratios, we then realized that is equivalent of what was proposed in an earlier paper by Levina and Bickel. We are in 2005. There is a difference between the way they suggest to combine those ratios of distances and how we combine the information collected from multiple ratios evaluated for multiple points. The important thing is that we can measure the uncertainty which we estimate the intrinsic dimension. And the difference between QUT and the 2 nearest neighbor is that the 2 nearest neighbor was relying on a single ratio of distances for each data point, while QUT consider consecutive, C stands for consecutive ratio, to build the intrinsic dimension. So we look at the larger neighbor of every data point. This imposes a constraint because we now need to assume that the intensity of the Poisson process has to be constant over this larger neighbor, not just on the ratio, on the length of the second nearest neighbor, which is what the 2 nearest neighbor estimator uses, but on the length of capital L, the largest nearest neighbor that we consider in building the QUT estimator. So this is in some sense a drawback, but the advantage is that we are robust to noise in the data. Then Francesco manages to prove that not only the ratio of consecutive nearest neighbors, so 7 to 8, 8 to 7, or 20 to 19 as a well-known Poisson distribution, but it derived the expression of the distribution of the ratio of distances of neighbors of any 2 orders. So N2 to N1, with N1 smaller than N2. So we now extract from the data another summary statistics, which is what we call mu dot, which is the ratio of distances from the N2 nearest neighbor to the N1 nearest neighbor. Here's the expression for the distribution, where B is the beta function. And Francesco derived also the kth moment of this quantity mu dot. So here starts a work in collaboration with Francesco, again, Alessandro Laio, and Diego, who is a PhD student of Alessandro, whom I forgot to mention at the beginning, but there's a reference to the joint paper. So using this quantity, well, we can derive from the kth moment the first and second moment, the mean and the variance of mu dot, and the distribution of this mu dot when we have N1 equal to some value, say 10, and N2 equal to 2 times 10. So when the ratios are one, the double of the other. So the 10th nearest neighbor to the 5th, the I don't know, the 30th nearest neighbor to the 50th nearest neighbor. And from this distribution and its moment, we derive the GRIDE estimator. So the advantage of using GRIDE, or the distribution of mu dot relative to the one that we use for the first nearest neighbor, is that those distribution as D, the intrinsic dimension varies, those are the different colors, are less overlapping. Here is the Pareto distribution with different values of D, which is the scale parameter of the Pareto, which for us is the intrinsic dimension. And you see that they are very overlapping in the tails. When we look, instead of the second to the first nearest neighbor, at the fourth to the second nearest neighbor, the distribution as D varies are more distinct. And this allows us to better estimate the intrinsic dimension. Here is the 64th nearest neighbor to the 32nd nearest neighbor. So those distribution as D varies become more and more separated. And here is 512 nearest neighbor to 512 divided by 2, which is 256. So this is the advantage of working with GRIDE relative to the original Pareto distribution. And here is a plot that shows you what are the nearest neighbors distances considered in the two nearest neighbor in CRIDE and GRIDE. So those are points from our Poisson process. We select 4 of them at random, but at the end of the day, we will use all of them. The two nearest neighbor looks at the first to the second nearest neighbor ratio of distances, okay? And you need the density of the Poisson process to be uniform over this very local scale. The advantage of going to GRIDE is that more nearest neighbor are considered. Here, as we look at capital L equal to 40, we look at the 40 nearest neighbors and all the ratios for every point, blue point, we look at all the distances up to the 40th to the 39th nearest neighbor. And of course, we need the density to be constant over this larger ball. And here comes GRIDE when we look at the ratio of the 20th to the 40th to the 20th nearest neighbor. So again, the same 4 points. And in red, you look at the 40th to the 20th nearest neighbor. So GRIDE uses the information on the ratio of those distances. And we need the density of the Poisson process to be constant over the ball of radius 40 if we look at N2 equal to 40. So here you envision the 2 things besides this uniformity assumption of the Poisson process, which is less stringent here and equally stringent between GRIDE and CRIDE, because you need it to be constant over the ratio of over the distance of the 40th nearest neighbor if we set L equal to 40 and N2 equal to 40. But on the other hand, we can say something also about the independence assumption. Since to build our estimator of the intrinsic dimension, we collect information not only for those 4 highlighted data points, but from all the data points. Sometimes those data points do share nearest neighbors, okay? So, and it's more easy that they share nearest neighbor in the 2 nearest neighbor and in the CRIDE, because for example, here you already see that those 2 data points do share one of the 40th nearest neighbor and actually even more than one, okay? So this violates the underlying independence assumption that we make. This independence assumption, it's harder to be violated in GRIDE because it's much harder for points to share the 40th, their 40th nearest neighbor and their 20th nearest neighbor, which is what enters in the estimator of the intrinsic dimension with GRIDE. So 2 nearest neighbor, CRIDE and GRIDE. I know the names look a little equal, but those were the acronyms that we came up with. And the two assumptions that play differential role in our estimator are the independence assumption and the uniformity of the density. The other advantage of working with CRIDE and GRIDE relative to the two nearest neighbor is that they are more robust and allow us to noise first, because data are collected typically with noise. So even if, for example, in this picture, these are three-dimensional data collected that really live on a two-dimensional manifold, okay, which is this line. But careful, there's noise around the data. So data are not really aligned around this blue line, but the noise makes the data scattered around this line. So the two nearest neighbor is tricked by this noise and believes that the data, for example, here is collected in a two-dimensional manifold. If we look at this subset of the data, because what we see is, yes, a line, but the noise makes it look like the data is two-dimensional. Or if we look at the data point in this region of the space, it seems that the data is three-dimensional, genuinely. On the other hand, if we look at the old picture, we realize that the data is really one-dimensional, and what makes it look like two or three-dimensional is the noise. So CRIDE and GRIDE are more robust to noise and allow us to study how the intrinsic dimension varies as we look at the data at different scales. So here in this picture, those three circles are looking at the data at different scales. Here is a small scale, here's a slightly bigger scale, here's an even larger scale. So when you have the data, you never know at what scale you're looking at the data. So it's important to have an estimator that allows us to study the intrinsic dimension as the scale changes, the scale at which you look at the data. So to sum up, there are so far three estimators: the two nearest neighbor, GRIDE and CRIDE. Two nearest neighbor only looks at ratio of the second to the first nearest neighbor. CRIDE looks at ratio of the Lth to the L-1 nearest neighbor. The positive aspect is that there is a closed form expression of the density, and that CRIDE, we can prove that it has a lower variance as an estimator for the intrinsic dimension than the two nearest neighbor, but needs rho to be constant on a larger scale. The negative aspect is that because we look at a larger neighbor, there can be overlapping region, and this induces dependence, which is something that we don't want. And then we came up with GRIDE, which is sort of a compromise between the two nearest neighbor and CRIDE. It looks at a ratio of the nth second and the nth first nearest neighbor, when n2 and n1 can be anything. The positive aspect is that the probability that shared nearest neighbors across different data points is lower, especially if we take n1 and n2 to be large. The negative aspect is that here we do not have a closed form expression of the estimator of the intrinsic dimension. So we need to rely on numerical optimization to find the estimator, and to bootstrap to find a measure of the uncertainty. And the positive thing is that the variance of GRIDE reduces as n1 and n2 increases. And higher order estimator have less bias. So GRIDE is a good compromise between the two and the CRIDE nearest neighbor. So this is all nice. Remember that here we can handle only the case where we have a single submanifold that contains all the data points. Here's something I've told you already, the trade-off between homogeneity and independence assumption in the three estimators. I've been over this, over the picture. Now let's move to a setting where instead of a single submanifold, of which the intrinsic dimension is what we are trying to estimate, we have for example, in this picture, 3 submanifolds, each one with its own intrinsic dimension. So the points here are not collected in a 3-dimensional space, but there are a subset of points that live in a 2-dimensional space, another subset of points that live in another 2-dimensional manifold with a different inclination, and another subset of points that is generally collected in a 3-dimensional manifold. So here we'd like a methodology that tells us, look, these points is really embedded in 3 submanifolds of dimension 2 again, but with different inclination or direction, and 3. And we want to know which point belong to which submanifold. And here we come up with Hidalgo. So Hidalgo is something that I told you already in my previous talk about 2 years ago. And I will only give you the underlying idea. So in Hidalgo, we go from a single Pareto distribution to a mixture of Pareto distribution. And K, the number of components in the mixture, identifies the number of submanifolds. So this is the interesting idea behind Hidalgo, going from a single Pareto to a mixture of Pareto distribution. And we are Bayesian here. We put some prior distribution on now D, the dimension of the single submanifold, and P, the mixing probabilities in the mixture. And besides being frequentist, we can also be Bayesian. So we put priors on D and P. We enlarge the mixture with latent variables, and we crank the Bayesian machinery. We have well-known methodologies to estimate those intrinsic dimension of those K submanifolds. And remember, N is the entire collection of data. So the prior are gamma for D, Dirichlet for P, and then we have those latent variables Z. We assume a discrete distribution. We can work out the posterior and everything works, except that we realize that we need to add another assumption, which is an assumption of local uniformity. That is, if this green point has some intrinsic dimension, we would like to think, and this seems reasonable, that points close to this share the same intrinsic dimension. So neighboring points are more likely than not to have the same intrinsic dimension. So to enforce this assumption of local homogeneity, we need to introduce an n by n proximity matrix, curly n. So this will become part of our likelihood. So the likelihood, besides the mixture of Pareto distribution, has this additional information extracted from the data, which is this proximity matrix. And then we crank our Bayesian machinery and we can do what we really wanted. So identify how many submanifolds there are, what is their intrinsic dimension. Now, let's move on to the applications. We, at this stage, have quite a few applications, all very interesting. I'm gonna go over some of them. In molecular dynamics, we have configuration of proteins that move from a folded to an unfolded state. In particular, we have 32,000 configurations, so this is N, and data is collected in 32 dimensions. Here we identify 4 submanifolds, of 3 of them of low intrinsic dimension, 12, 13, and 13 point something, and 1 of higher intrinsic dimension. And it turns out that when the protein is in a folded state, most of the time it lives in the manifold dimension. Okay, so let me move on the applications that we did with the colleagues from QUT. Okay, so the one with Edgar, Kerry, and Francesco uses the fact that these days we have sensor tracking data technology that allows us to capture 25 frames per second the coordinate of each player and of the ball in during a game. So we can go from a static summary statistic description of a game to a dynamic analysis, and the intrinsic dimension methodology allows us to do that. And specifically, we look at data from NBA season 2015-2016, and we realized that factors affecting the success of a play, whereby play we mean an action with ball possession by the team, depends crucially on the placement of the players. This is something that we know, the versatility of the attacking players, and is affected by coordinated unpredictability, which is a notion that contrasts unpredictability of the players, but in an unorganized or chaotic way. So we analyze data both within plays, between plays, and between games. Okay, interesting features were highlighted by using the intrinsic dimension methodology. So specifically for movement data within play, here you can see the type of data that we've been working on. Here we have 3 players, the blue, the green, and the orange one, plus the ball, okay, which is the red trajectory. So looking at this data, we the intrinsic dimension managed to translate complex movements dynamics in space and time for the 10 players into a more coherent statistics. Here you see the heat map of movements on the bottom, and the intrinsic dimension posterior, median posterior, as it changes over time. So here we see that the methodology, our intrinsic dimension methodology, identifies 4 clusters in the plays, and as the play progresses, the intrinsic dimension first is low. Here is the attacking team moving forward. Here the ball is passed, and then space is made to allow the shot to take place. So I won't go into the detail. The paper is online, and we are currently revising it for as minor revision for the Annals of Applied Statistics. Then we also look at the intrinsic dimension as it evolves with time over more complex blue and more simple plays. And it turns out that in simple plays, the intrinsic dimension is below 5 typically. So those are 3 plays of a simple type. Over more complex play, the intrinsic dimension is typically bigger than 5, but about 8. Here on the y-axis, you have the intrinsic dimension. On the x-axis, you have the timestamp. And what I mean by complex and simple play, here's the a simple play, how the 5 players and the ball move around in a simple play. Here's a complex one, and you probably from the picture realize what I mean by simple and complex. Then we also use the intrinsic dimension of the shot cards. Here is of a play where Cleveland is in attack. A shot card records the position of the players in the attack team at the time the shot is taken. And the shot can be a score or a miss shot. And here you see that our methodology allows to identify 3 very distinct clusters. This is the heat map. So as the color is more yellow, those points are clustered strongly together. So let's look at the second cluster. In this second cluster, most of the shots are missed and only a few are hits. So this is useful for coaches that by analyzing our analysis can learn what happened in those shot cards with reference to the position of the players that went wrong, because most of the time the shot was missed. And finally, here we analyze the intrinsic dimension of winners versus losers in 15 separate matches. And it turns out that winners tend to have a higher intrinsic dimension overall in the game. I will not go through explaining what the picture is about, but this is the final outcome of our analysis of different games. So with the intrinsic dimension methodology, we managed to identify different stages in offensive actions. We can translate complex movement patterns into a more coherent dynamic statistics. We can identify cluster in shot charts, giving a lower versus a higher return in terms of scoring or non-scoring. And we can guide in planning more effective attacking and defensive plays. And a few seconds on the other application with QUT.
Just one more minute, Antonietta, so that we...
Yes.
Okay.
Can you hear me?
Yes, yes, can hear you. Just for one more minute, and then we'll have a time for one question, and then we'll finish.
Sure. Okay, so well, this is an interesting application with Abhishek Varghese, again, Francesco and Carrie. Here we analyze COVID data over the entire world and over more than a year time, starting from March 2020 to May 2021. And we can, in this case, cluster different countries depending on their response to the pandemic. We clearly identify two submanifolds of distinct intrinsic dimension. Here, the data is collected over a very high dimensionality because we have data over time referring to daily new cases per million, daily new deaths per million, and government stringency index that tells us how each government responded to the pandemic. And our methodology allows us to identify two distinct clusters depending on how those curves move in time. So I think we can stop here. The beauty about intrinsic dimension is that now Francesco Denti has an R package. It's called Intrinsic. It's available on his GitHub repository and allows you to estimate the intrinsic dimension with pretty much all the methodologies that I told you about. The two nearest neighbor, GRIDE, and Hidalgo. And many papers have been already published, some in very good journals, generalist journals like Science and the Nature Scientific Reports. And some have been submitted and we are waiting to hear back. And we hope that you will also pick up this methodology and use it in your data. Thanks.
Thanks very much, Antonietta. That's an excellent presentation. Who has some questions? We have time for just one or two questions.
I'll ask
yes, David.
If you can hear me.
Yes.
Yes.
Thanks, Antonietta. That was a really interesting talk and interesting method. Are there any constraints around the distance function? So, for example, if I have something on a directed graph where it may not be symmetric, is that going to be a problem?
No, it's not a problem. It needs to be a proper distance. So typically, it needs to be a distance. So with the three typical requirements that a distance should have.
Okay. Triangle inequality and symmetry.
Yes.
And stuff. Yeah.
Yes. So, but I don't think symmetry has to be a strict requirement.
Mhm.
Okay, so certainly triangular inequality, you need to have it. Thanks, interesting question. I don't think you need symmetry.
Okay.
So working on a graph with distances defined on a graph should not be an issue.
Great.
But I will get back to you about this. I need to be positive about the answer that I'm giving.
Thank you.
Okay, thanks, Antonietta. We have a question from David Lovell.
Hi, Antonietta. Thank you so much for your talk. I really enjoyed it. I'm just curious to know if with the underlying Poisson point process, you need to be mindful of its intensity relative to the curvature of the manifold. I can just imagine situations where if that Poisson process isn't sufficiently intense, you start to see a connection between points that are distant from each other on the manifold. Do you see what I mean?
Yes, yes, absolutely. So if the data are dense, there's no issue in using GRIDE or CRIDE. If the data are less dense, you need to be more careful on how you interpret the results, exactly because of what you're pointing out. So in this case, the 2 nearest neighbor is best.
Okay, thank you so much.
Yep.
Okay.
Thanks.
Thank you very much. We're out of time now, and I know there's a couple of people who still want to ask questions, so perhaps Antonietta can take them offline. But for now, we need to draw this to a close, and I'd like everybody just to applaud in the usual sort of virtual way, either through the emojis or else give a unmute and give a round of applause. Thanks very much, Antonietta, and thank you very much to all the audience. All right, thank you very much. We'll call it quits.
A real pleasure to be here. Thanks.